Screen hide. Uh, Hello. Very good evening to one and all who are attending this webinar. I am Partha Sarathi, Associate Professor in Aeronautical Engineering Department, MLR Institute of Technology, Hyderabad, India. Welcome to you all. Today's my topic is a method for tuning more number of students towards outcome-based education. With an example, I would like to quote. Today's agenda is, first I'll discuss with abstract, what is the motivation towards OBE, and the next one is addressing the current issue, and I'll take one example on single topic, that is first law of thermodynamics, proceeding further with the Bloom's level, and what output I have achieved by implementing this method that I have represented in the output. Let us go through with abstract. One of the best ways of tuning good number of students in a class to follow outcome-based education is directly to make them read many textbooks and solve maximum possible numerical problems based on real-time applications. This is the topic which I have chosen. Here, what I would like to address is, more often students will read many textbooks. We know that. But how many of the students are reading the textbooks? That is the first question. Second point is, how many students are solving more number of numerical problems based on the real-time applications? That is another issue which I am going to address here. Let us consider one example, say first law of thermodynamics. Recollecting the statement, that is remembering the statement, it is nothing but as energy can be neither created nor destroyed, but can be transformed from one form to another. If we teach this statement to the students, definitely they will try to remember it and reproduce it. With that, we can't achieve the OBE. So what I did is, I have closely observed the statements in the perception of the student and trying to understand the importance of the some terms, like I listed energy, sources of energy, energy types, conservation of energy, existence of energy, and mechanisms of energy. We think energy is the single term. As a student, if we think energy is the single term, okay, I understood this concept, like that he will think. But he has to understand, as I said, all those terminology associated with the energy. That is our part to do, the mechanism, how we can implement into the mindset of the students such that they can clearly understand the statement of the first law of thermodynamics. After that, let us focus on applying to the real-time engineering applications, like first law applied to different types of systems and flows. This part I would like to discuss with you with the help of some pics, so that you will clearly understand how I have integrated with the application level of the Blooms. After that, we have to make them analyze first law by giving some simple examples, which I will discuss you in the meanwhile. That is, they have to follow the established connections to different applications with respect to first law. And then leave them for their self-analysis. This will make them to walk through evaluating, evaluating and creating levels of the Blooms pertaining to first law of thermodynamics. In the coming slides, you will come across how they have studied and how I have implemented this Bloom's level up to 4 levels, and how I left 2 levels, that is evaluating and creating levels for these students for their self-study, which gave me some result that I am going to show you now. The motivation for this webinar is I have done a lot of exercise to attain COs and POs in terms of documentation. Parallelly, I came to know that I have to do some other thing such that I can attain better COs and POs in my particular subject. So in this regard, what motivation I got is, parallelly, if we can focus on the student mindset by tuning more number of students towards OBE, then attainment of COs and POs will become easier. For that, what we have to do? We have to mold the students in such a way that they work towards OBE. How? That means you look into the term OBE. O stands for outcome. What is this outcome? Then I thought all the activities and events performed by the students are more or less related to outcome alone. So this is the motivation for me to go through. So let us consider one issue here. Typically, if you consider a class consisting of 60 students, no doubt 10 students performing very well, they will obviously reach outcome-based education. But if you consider 25 students performing median level, they feel it is very hard to reach OBE. Even we also feel the same thing. Similarly, 20 students performing at lower level, they are unable to reach the outcome-based education. No doubt 5 students, no performance, no OBE at all. This is an assumption which I have taken. In that, I have focused. Now we can focus on 25 plus 20, 45 students, that is, who are unable or feeling hard to reach OBE. We have to identify those students. Those students are resource for our OBE. And if you closely observe those students, can't they reach the OBE? Definitely they can. But what is their nature? That we have to observe. What I observed in those 45 students is they always want to learn. They have the zeal to learn. They don't know the path to study properly. Sometimes they used to struck up. They work very hard, but not smart. In this regard, by motivating them towards Bloom's level study, I observed 8 more students in the last academic year reached to OBE. That is, out of 45, 8 students has achieved this outcome-based education. That means creating level and as well as evaluating level. They have reached by themselves. So this I am going to address you in the coming slides. Let us consider one example here on a single topic. Once the students start reading any textbook on a single topic, say he or she finds some large number of pages on that particular topic. It may not be true for all the cases, but sometimes they will observe large number of pages to be written and also finds more number of numerical problems to be solved. Then they feel it very difficult. It's all because of many concepts involved in it, which we know, but they don't observe carefully. Let us consider one example, that is first law of thermodynamics. Take some textbooks, how this topic has been addressed, in how many pages they have addressed. Let us go through here. Firstly, when you take thermodynamics and engineering approach by Eunice Senegel and Michael Bowles, first law of thermodynamics starts from page number 51 to 109, 50 pages. An average student, when he sees these many pages, he will read 3 or 4 pages and then he will leave it as such. If you take another textbook, say for example Engineering Thermodynamics by R.K. Rajkot, first law of thermodynamics page number starts from 101 to 226. That means more than 120 pages are corresponding to only first law of thermodynamics. So they look into the volume rather than the concept. So I am addressing here. If you take another textbook, Thermodynamics by Henry J. Jackson, same first law starts from page number 9 to 12. But always in many pages, he used to address the first law, meaning of the first law, application of the first law, how to analyze the first law in many pages. Let us consider with the terms of Pekenag, thermodynamics solved problems by Pekenag. Page number starts from 15 to 53, all numerical problems solved. Students used to read this in many number of pages and they used to solve the problems, but they are not understanding the exact analysis or evaluating or the concept lies behind this. Here the area which I have chosen to pull more number of students to work upon towards OBE, which stands here. Now let us consider level 1, how we are going to address. Recollecting the statement, that is remembering the first law of thermodynamics, energy can be neither created nor destroyed, but can be transformed from one form to another form. When we state this, he will by heart or he will try to understand on his own to a certain extent. If we keep some figure here, say a person pushing the almara say of 90 kilos, he needs some energy. How do we get the energy? That energy, say for example, he has taken burger and it has converted into chemical energy inside our body. Then he got the energy, he pushes the almarase. That means he is doing some work, which I represented as W with forward arrow mark, and at the same time he is liberating some energy, heat outside, which I have represented vertical arrow mark as Q. With this example, you can say that a chemical energy can be transformed into work. Work is a form of energy. Heat is also a form of energy. So the term transformed, you can stress here with this example. Here, with this, we should not stop teaching. We have to address those 45 students which I have earlier mentioned. I am going back to the previous slides, please. Red color, I have represented 45 students, right? So now you observe those 45 students and ask them to give the assignment that unique example you have to pick up, which validates this statement. If we can do this kind of exercise, in the next class, whatever we are going to teach, they will understand in a better way. That means you have to pick up five students like that and ask them to give unique example for this alone. Then you can start giving some other topic or some numerical problems here based on this. Excuse me. Let us consider one problem here. A mass of 8 kg gas expands within a flexible container so that the PV relationship is of the form PV power 1.2 is equal to constant. The initial pressure is 1000 kilopascal and the initial volume is 1 meter cube. The final pressure is 5 kilopascal. If specific internal energy of the gas decreases by 40 kilojoules per kg, find the heat transfer in magnitude and direction. This is the problem I have given for the students. what happens here is he has to remember the formulas. What all the formulas we have taught, that he has to recollect and represent here. The first formula here, what I'm addressing is Q is equal to delta E plus W. At the bottom you can see, find the heat transfer in heat transfer, that is stands for Q, delta E stands for internal energy, plus W stands for work done. Now he has specified in the problem itself that specific internal energy of the gas decreases by 40 kilojoule per kg. So that I have represented it as delta E is equal to minus 8 into 40. Why we have used minus 8? Because mass is of 8 kgs. Last but one line you can see minus 8 into 40, that is minus 320 kilojoules. And here we said gas expands, so the corresponding formula he has to remember. What is that formula? Work done formula. Because see, in heat transfer last line, Q is equal to delta E plus W. Delta E you know, W you don't know, so W formula he has to recollect. For gas expansion, the process here it is given as polytropic process. PV power n is equal to constant. So W is equal to P1 V1 minus P2 V2 by n minus 1. So once he substitutes this formula, he knows some variables, that is P1 V1 P2, but he don't know V2 value, but he knows n value. He has to evaluate V2 value. For that what he has to remember again, he has to establish the relationship between P1 V1 T1 at the initial level, P2 V2 T2 at the final level. So the first line of the answer stands here. T2 by T1 is equal to P2 by P1 whole to the power of n minus 1 by n is equal to V1 by V2 whole to the power of n minus 1. If we start reading the formula like this, definitely these average students may not able to understand. So for them, the remembering concept how we have to frame here is establish two equations. That is, first equation is P1 V1 by T1 is equal to P2 V2 by T2. Establish another equation, P1 V1 power n is equal to constant, right? So P1 V1 power n is equal to P2 V2 power n. That formula you correlate it, solve those two equations, and you will get the relation T2 by T1 is equal to P2 by P1 whole to the power of n minus 1 by n, V1 by V2 to the power of n minus 1. That means here, if you closely observe, it stands for, though the problem appears lengthy, or 8 or 9 lines, but he has to remember the formulas. How to remember the formulas? This all comes under first law of thermodynamics only. So if you teach in this way, that means a single problem, if you teach in this way, then they will think that, okay, first law is not alone a single formula, it is having some other concepts which we have to recollect. That I made it here. Here he is recollecting in this single problem, he is recollecting almost 5 formulas. This is the first level of remembering those who are studying at the engineering level. Let us go for level 2. After remembering, now make them observe closely the statement of the first law, that is, energy can be neither created nor destroyed, but can be transformed from one form to another form. It is also called as conservation of energy. That means all the terms associated to energy. So now in this level 2, that is understanding level, first he has to know what is energy. Give one example as shown here. A woman is running. If you give such kind of examples, they will think, okay, energy is something which we know pretty well. Now ask the students to list some more energy in the class itself. they will open their mouth and they will start rethinking and trying to understand, correlate with the statement. Then jump to sources of energy. List some sources of energy, 2 or 3. Say for example, light is a source of energy, heat is also a source of energy, motion is also a source of energy. Ask them 2 more sources of energy to list. With that, an interactive session opens. Now, pull them to what are the types of energies. If you say that so many types of energies are available, ask them to list. There is a deep meaning here. It is not the simple figures which I kept here. And when you look into understand and level 2 and level 4, there is a close relationship. Level 2 and level 4 is having a close relation. Whatever they understand here, they have to analyze in the 4th level. So that I will tell you in the 4th level. Now here, if you observe the types of energy, I have listed some: magnetic energy, kinetic energy, heat energy, light energy, potential energy, chemical energy, sound energy, electrical energy, nuclear energy. Now stop immediately, ask them to list some more. They will start thinking. If they couldn't able to say, ask them to write a short note on each types of energy. Then our discussion will be walking through OB. That means they will try to think of first law of thermodynamics when you ask energy types. Now let us enter into another form, conversion of energy. So they already know that conversion of energy means heat can be converted into work, work can be converted into heat. Like that, they might have read some textbooks in school days. Now you give some different example like this as shown in the figure. A kinetic energy with the example of one person bicycling there, reaching the hill and getting down from there. If you closely observe, he is taking a lot of energy. A lot of energy is required while climbing, and while getting down from the hill, lot of energy will be released. That means kinetic energy converted to potential energy again converted to kinetic energy. If you give this kind of relationship between conversion of energy, then they will start thinking in another direction. That means here we are focusing that how best we can tune the students towards OBE. Now, ask the students to do some exercise on this conversion of energy. How many types of energy conversions are existing? List them if possible. Start them discussion. Ask them to discuss something in the next class. Now let us think into existence of energy. So when you see the figure here, nucleus, electrons, electricity, something like that. Now, you have to observe closely the figure. It represents that whenever you put such kind of figure, student immediately thinks that yes, electrons, protons I have studied in school days. I might have forgotten, but I have to revise it because energy is existing there. That is useful here in the first law of thermodynamics in the form of a charged particles. So whatever I studied earlier, that I have to recollect it. With a small figure, you are giving that much information. That means existence of energy also they have to understand. Then let us go into another point known as mechanisms of energy. Consider a simple example: a kettle with some water having hold it in handle. Fire is coming beneath the vessel, which means that radiation is there. Some black color arrow marks inside the kettle, you can see that is representing convection. And you can see the heat flows through the handle, that is conduction. So the here mechanisms of energy means I have taken example heat energy. Heat energy can be represented in the form of conduction, convection, radiation. So this is the mechanism which they have to understand. If you take electrical energy, then they have to correlate like this so many times. That is what the understanding level corresponding to first law of thermodynamics. Now let us go through after completion of this. That means you give some examples to them and give assignments to them such that they will come up with some examples. With that examples, let us solve some problems. Say a system composed of 2 kg of the fluid which expands in a frictionless piston and a cylinder machine from an initial state of 1 megapascal 100 degrees centigrade to a final temperature of 30 degrees centigrade. If there is no heat transfer, find the net work for the process. In this example, if you closely observe, find the net work done. Students often used to rush solve the problem immediately, as though they think that we know everything. So often they used to attempt like this. The moment work done calculation comes to the students, they will start thinking of entering into the one formula known as W is equal to integral PdV, which is represented in many textbooks. But the understanding level is given below. It is given that you are dealing with first law of thermodynamics, so which states that Q is equal to delta E plus W. Here there is no heat transfer, Q stands to 0. So W is equal to minus delta E, which you can rewrite it as minus du, which is nothing but as a change in internal energy. The internal energy here corresponding to U is equal to Cv delta T. So integral 1 to 2 Cv delta T comes into the picture. This is where the students has to understand the meaning of the internal energy. That means applying the formula also stands under understanding level. W is equal to minus 1 to 2 Cv delta T. You know Cv value 0.718, T1, T2, it is in the given data 100 minus 30. Collectively you will get minus 50.26 kilojoule per kg. This system is composed of 2 kg matter. So that if you multiply for the total work, you will get minus 100.52 kilojoules. Here minus stands for the work is done into the system. That means we are covering the concepts pertaining to the first law of thermodynamics before itself. Now let us enter into another example wherein which he can understand clearly how to represent, how to understand heat and work interactions with respect to two systems. Take one example here, one problem. During one cycle, the working fluid in an engine engages in two work interactions, that is 15 kilojoules to the fluid, that is W1 is equal to minus 15 kilojoules represented towards the system in the figure, and 44 kilojoules from the fluid is represented arrow mark outside from the system. W2 is equal to 44 kilojoules, and three heat interactions, two of which are known as 75 kilojoules, which is inside the system towards the system, and 40 kilojoules from the fluid, that means outside the system. Evaluate the magnitude and direction of the third heat transfer set, that is Q3 you have to evaluate. We know that whether Q3 is towards the system or outside the system, that you have to evaluate. Once you can evaluate this, means thorough understanding of the heat and work interactions will give you the sign for this. From the first law of thermodynamics, sum of all heat interactions is equal to sum of all work interactions. It may be to the system or from the system. Now as shown, Q1 plus Q2 plus Q3 is equal to W1 plus W2. Substitute all those formulas, evaluate Q3. It is came as minus 6 kilojoules. That means Q3 is coming out from the system. That is, it is rejected from the system. This way, if the student can able to understand, means it's very easy for us that we can walk through towards OBE. Once, if we can solve the problems in this way with the examples, definitely after going home, they will start reading the textbooks. But while we present, first itself, we have to follow the textbooks, then only they will come to know that sir has taken this example from this textbook, that example from this textbook, like that. So now let us go for next level. The questionnaire can be addressed at the end, please. Then focus on applying to real engineering applications, like first law applied to different types of systems and flows. Applying. How this first law is applied? Let us consider water heater here in the left side. That is system. Control volume represents the system. And flows means here, you see a person holding the hose pipe, garden hose pipe with a nozzle, filling the bucket with water. Now here, water is flowing through nozzle. The first law is applied over nozzle. These are the two types of applications which we can address to them. So let us consider one example here and walk through fast. A room for 4 persons, the room is indicating system, has 2 fans, each consuming 0.8 kilowatt power and 3 100-watt lamps. Ventilation air at the rate of 8 kg per hour enters with an enthalpy of 84 kilojoule per kg and leaves with an enthalpy of 59 kilojoule per kg. If each person puts out heat at the rate of 630 kilojoule per hour, determine the rate at which heat is to be removed by the room cooler so that the steady state is maintained in the room. Here what I am addressing is not the problem. Try to think. We are giving some example, numerical example to the student, which is real-time application. In a single room, 2 persons, 3 fans, if we say like that, he will get more impressed. Yes, it's a practical thing he's addressing. Like that, a steady state means what? He will directly understand from this example, W1 is equal to W2. W1 is nothing but as the flow rate, air flow rate, 80 kg per hour, which can be converted into seconds. That is 1 by 45. W2 is equal to 1 by 45. That means we have maintained the steady state. Enthalpy is changing H1 to H2. Here, now once you give this much information, that is more than enough rather than formulas, what I feel is here. So real-time applications we are stressing over here. So when you address water heater, don't put the water heater example itself. They will listen and they will forget immediately. So if you give some other example like this, definitely the student learning capability will be increasing. Take one more example. In an air turbine, forms part of an aircraft refrigerating plant. We are integrating refrigeration and aircraft also. Air at a pressure of 295 kilopascal and the temperature of 58 degrees centigrade flows steadily into the turbine with a velocity of 45 meters per second. The air leaves the turbine at a pressure of 115 kilopascal, a temperature of 2 degrees C and the velocity of 150 meters per second. The shaft work delivered by the turbine is 54 kilojoule per kg of air. Neglecting changes in elevation, calculate the magnitude and sign of the heat transfer per unit mass of air flowing for air. Take Cp value 1.005 kilojoule per kg Kelvin, and the enthalpy H is equal to formula CP T. Okay, what we have to evaluate here is a turbine. We are representing it here. Inlet conditions, outlet conditions, we are representing it here. And we are giving here steady flow energy equation through which they could able to evaluate the magnitude and sign of the heat transfer. Sign means direction of the heat transfer. The formula is not the important thing. What they have to observe is, it's very simple that we can apply this first law by looking into some numerical examples. That is the feeling which I have developed inside the students with this kind of examples. Now let us go for level 4. As I said, level 2 and level 4 both are correlated. After applying, make them analyze first law by simple examples like establish connections to different applications with respect to first law and leave them for self-analysis. Means, now consider one example here which I have quoted. Electrical energy is converted to mechanical energy. That means, what is the connection here in mechanical energy and electrical energy? You will think here. Now, so if you would like to convert electrical energy to mechanical energy, you need a support of motor. If you would like to convert mechanical energy into electrical energy, you need a dynamo. Our statement states that energy can be transformed from one form to another form. First law of thermodynamics. One form to another form. Okay, that is mechanical energy, electrical energy. Here, you could able to see if the student is understanding this level, then they will start analyzing. You consider thermal energy to electrical energy, thermocouples are required. Electrical energy to thermal energy, heater is required. That means all the Bloom's levels are correlated one by one. So let us take one example. I am leaving as such sound energy, light energy, and chemical energy for yourself understanding. So how it can be analyzed if we give some problem, say real-time problem. Let us consider a site evaluated for a wind farm is observed to have a steady winds at a speed of 8.5 meter per second. Determine the wind energy per unit mass for a mass of 10 kg and for a flow rate of 1154 kg per second for air. Now you look into the diagram here. The water is hitting the shore at a speed of 8.5 meter per second. Not the water here, the wind. If the wind is hitting the shore, that means wind is traveling at a speed of 8.5 meter per second. Then what is the energy level of the wind with respect to mass, unit mass? So wind is moving, we can consider it as a kinetic energy. So small e represents E is equal to K is equal to half V square. As we are going to evaluate for unit mass, M is considered as 1 half mv square. So you will get a value of 36.1 joule per kg. I have represented here the conversions here. And see, unit mass, you got an energy of 36.1 joule per kg. And if you give some kgs, say for example 10 kg of air, then multiply with 10, you will get 361 joules. And per second, if it is the mass flow rate is given 1154 kg per second, then multiply it and put some conversion there, you will get 41.7 kilowatts. Now with this, we are not solving the problem here. Try to understand carefully. We are not solving the problem here. We are trying to analyze by ourselves, and in the perception of the student, if you give analysis like this, stepwise analysis, you ask them to analyze stepwise, then they will come up with same energy 41.7 kilowatts. In a class, if you start directly saying that wind energy is 41.7 kilowatts, average students, most of the average students, they will, okay, numerically they will think, but physically they have to see, means you have to take through them such kind of examples, which I implemented here. So with this, so many students I have observed so many transformations in many students with this particular example. Let us go for another example. Very simple example I'm taking. Consider a 1200 kg car cruising steadily on a level road at 90 km ph. Now the car starts climbing a hill that is sloped 30 degrees from the horizontal. If the velocity of the car is to remain constant during climbing, examine the additional power that must be delivered by the engine. Most of the students, they might have driven the car. Within 5-10 minutes, I'll close. What they will think is, they might have driven the car in hill areas also, but technically they might have not analyzed that. By practical experience, they might have known something, but now if you take such kind of example and ask them to evaluate what is the additional power that is required while climbing the hill if it is maintained at constant velocity, means. So in the diagram I have represented velocity as 90 km per hour at an inclination of 30. So I have represented here mgv, mass 1200 kg, g we know 9.81 meter per second, v 90 km per hour, sine 30 degrees, and unit conversions I have represented, and we got 147 kilowatts, approximately 197 HP. That means around 200 horsepower additional power is required for the vehicle. It means if you understand this, means they can participate in many competitive examinations. They can estimate with simple thermodynamics, first law of thermodynamics, they can design their own cars. Now, I taught this subject since 2010 academic year. I have represented here all the academic years 2010, 11, 11, 12, 12, 13, 13, 14, 14, 15, 15, 16. At the initial stage, this is the Bloom's level: understanding, remembering, understanding, applying, analyze, evaluate, and create levels. In the first year, what I have observed is I am using first level, second level, third level alone. In the next year, that means in the 2010 and 11, I couldn't able to reach 4, 5, 6 levels. In 2011 and 12, still I am unable to, because I am adjusting the mindset of the students. I was thinking how better I can present this to the students. 3, 4, 5 levels I couldn't able to achieve. 12, 13, I have stressed much on level 1 and 2. So obviously 3 has reached to some extent. Similarly, in the next coming year, I have introduced 4th level. And in 2014-15, I tried to implement 5 and 6 levels, but I couldn't able to. So what I did is, in the last academic year, I have implemented level 1, 2, 3, 4 for the first law of thermodynamics, the second law of thermodynamics, and some important cycles. Then with that, I could be able to achieve level 5 and 6 by the students. The whole effort is by the students alone, and my contribution lies in first level, second level, third level, fourth level. I left for the students to follow level 5 and 6. But ultimately, I got 8 students, which I have observed recently. 8 students, they reached level 6 and they are doing some projects corresponding to thermodynamics. This is the blog where I kept for the help of the students, where I have referred these many textbooks. Still I am referring some more textbooks which I have not included here. This way I have kept all the material to the students before starting of the session itself, and that helped the students a lot. And coming to the conclusion, in this way I would like to implement the above said methodologies in teaching learning process for major topics. This method of teaching make them study more textbooks and solve more number of numerical problems without any stress. This I have observed directly in the class. Every time when I go to the class, students used to come with more number of textbooks, different kinds of textbooks and different numerical problems, and they are not feeling stress. And I feel that I mold the more number of students and make them involved in outcome based education. It is always possible, which I have implemented. That's all. Thank you for the sessions. Any questions, please?
Thank you, sir. Audience can type their questions through the chat window.
Okay. Okay. Welcome. Sir, can you hear me, sir?
Yes, sir.
Okay, fine.
Sir, one question is, what is your course objective and outcome?
Okay, sure. My course objective was to make the students design and develop one engine already existing. My outcome was the students in the level of second year itself, they have tried for inventing engine, existing engine. They try to prototype the engine and do some modifications for that and try to get more performance. They have made all prototypes of different engines which I have not taught in the class. New engines they have prepared, and they participated in many competitions and won the prizes. And my main objective is to make them aware that thermodynamics is the basic subject which will be helping to them in the coming semesters for better study in propulsion. That is, I am basically in aeronautical department, so thermodynamics is the basic subject for the aeronautical students to study further in propulsion. Now the students who are studying propulsion subject, they feel it more comfortable and easy. That is how I feel that I got the course outcomes. Yes, sir.
I think we should work on the terms of students many times to involve them in learning process.
Yes, sir. Means they have to study on their own. They have to look after so many textbooks, so many examples, problems. If they solve like that, whatever the doubts they are getting, they can solve by themselves. And in a group when they are working, this knowledge will help them a lot in solving the practical problems. This is the feedback which I got from the students also, passed out students. Even they are working in some companies, HVAC companies. Those students also, they contacted me and they have asked some basics again, and they gave me the information that your approach is good, sir. You do some small modifications like this, like this. I have taken the feedback from the students and I changed a lot of things in it. So that made me success in getting 8 students which I have represented towards outcome-based education.
What are the typical questions asked by students?
So, first question is when we show the engine animation, the first question which raised by the students recently is that, sir, why can't we reduce the time of exhaust? Why can't we reduce the time of exhaust? At the same time, why can't we put increase in the that means input of the air fuel ratio? In that engine design, they are asking the minute question. That means if you reduce the exhaust, what happens? What is the impact on the engine? That is the first question they have asked. And while solving the problems, why we should use a polytropic process or reversible adiabatic process, and in what context we have to use that, practically in which area that can be applied, in labs where we can study this, all these things they have asked me. And now they could able to observe that polytropic process, adiabatic process in the aerodynamics lab, that is wind tunnel. While they do perform some experiments on wind tunnel, they have observed that yes, in aerodynamics also thermodynamics is influenced, and its corresponding process we have learned in thermodynamics, and it is helping us in evaluating so many parameters like that.
What is your student's profile?
Means I didn't get you. Students profile.
I'll ask. Professor Shukla, you can clarify, sir.
Yeah, please, sir.
Male to female ratio and their background.
Okay, they are from maths, physics, chemistry background, BTech second year aeronautical engineering, and 30 girls are 30, boys are 30, 50 student, 50 ratio. Is it clear, sir?
Yes, sir.
Male female ratio is 50-50, sir.
The audience is thanking, sir. Thank you, sir. Those are all the questions. I will send you the recordings.
Okay, sir.
Thank you.
Thank you. Thank you, one and all, for attending this webinar.